Okay, so we just looked at the simple pendulum here, and we said for small angles, it will have simple harmonic motion, and that simple harmonic motion is given by the position here, will be A cosine of omega t times plus phi, the phase shift. Usually the phase shift, if we disturb it this way and then let go, the phase shift will be 0 if we start from there. Omega is the square root of g over L. You see, the frequency depends only on g and L. It doesn't depend on how far you pull it, provided that the angle is small enough. If the angle is large, then actually omega is a function of theta also. So it's not like the spring. The spring was exact, but this is an approximation. We have to use approximation. But again, in physics or all science, everything is really approximate. Even the laws of nature itself, like Newton's laws, they are good, and they're good for a certain range, for things that are everyday objects and not moving near the speed of light. If they start to move at the speed of light, then you will need special relativity. If they become too tiny, then you need quantum mechanics. If they are too tiny and too fast, then you need relativistic quantum mechanics. And it goes on and on. And so don't say, well, this is no good because it's an approximation. Well, everything in life is really an approximation. Even things that you think that are exact, I don't know if they're exact forever and for all ranges, because they haven't been tested for all ranges. So it's not science and math. They're very intimately connected, but they're not exactly the same. In math, you have exact things, but in science, you have approximations. And in fact, the art of approximation is mathematical, and it comes from these Taylor expansions and so on that you learn about or will learn about in Calc 2. And so they're very important. Okay. So let us take an example here, which I'm going to read. You have a 300-gram mass on a 30 centimeter long string. It oscillates as a pendulum. So you have the mass is 300 grams, and the length of this pendulum is 30 centimeters. So we're given this. L is equal to 30 centimeters. The mass is 300 grams or 0.3 kilograms. L is 0.3 meters, right? 3 meters, okay? So what happens to it? Let me continue reading it. It has a speed of 0.25 meters per second as it passes through the lowest point. And then it says, what maximum angle does the pendulum displace? So they say V maximum, let me put here V max, and write it down. V maximum is 0.25 meters per second. See, this example here, we could solve it using conservation of energy, but we're going to solve it using just what we know right now. This may be a more complicated way, but we'll use it. So here's the pendulum. It's swinging back and forth. When it's here, you see when it's here, V is equal to 0. And when it's here at the maximum displacement here, it's V is also equal to 0. But when it's here, V is maximum. It's either moving this way or this way. If it just came through here, it's moving to the left. And if it was here and then coming back, it would be moving to the right. But they said the speed is 0.25. So the speed here, V, is 0.25. And the question is, how far does it go to the right? How far from its initial position from here does it go? Where does it go here? Okay. Where does it go? And so let's see here. Actually, they asked about the maximum angle theta. What is theta maximum by which it would stretch? It will move. Well, we will say we will have here. We have this function here. The velocity is 0 at the top, and it's maximum. So let's take. If we take the derivative of this to get the velocity, we will get x will equal. We will get the velocity. So let's see. We get the velocity. Let me write it. Velocity is equal to a omega with a minus sign times the sine of omega t plus phi. right? You take the derivative of this. Now the maximum velocity, forget about the sign, it just oscillates. So if you want to find the maximum speed, it's just what's in front, which is a omega. That's v max. So let's find the amplitude. So the amplitude will be v max over omega. The amplitude will be v max over omega, because I'm just forgetting about the minus sign and the sine function. Because the sine is something that fluctuates between +1 and -1. I want just the magnitude of the maximum velocity. It's here, it's either plus 0.25 or negative 0.25, but that's the speed, 0.25. So V max over omega, so it would be 0.25 divided by omega. You see the mass doesn't even enter. Omega is the square root of G over L. Square root of G over L. So let's find omega and then divide by it. So it would be G is 9.8 divided by the length. The length is 0.3. And then we have to take the square root. So omega happens to be 5.715. So 5.715. And what do we get for the amplitude? The amplitude we get 0.298. 0.298 meters. That's the amplitude. That's how far to the right it will be. Right, this is how far it will be to the right. That's x. But x is equal to L times theta. Remember from here. From here. I drew it here. Yeah, x is equal to L theta. So theta will be x divided by L, and we get theta. So theta will be x maximum, the amplitude, divided by theta, divided by L. Let me put amplitude divided by L, theta maximum. And so you take that 0.928 and divide it by the length. And the length is 0.3, so divide by 0.3, and we get 0.992. So theta is 0.992 radians. And I think I made a mistake here. Yeah, this sounds a little too bad. 0.25 over 5 something should not be larger. It should be less than 0.25. So yeah, so this number here is wrong. Let's do it again. 0.25 over 5.715. 0.25 over 5.715 gives me 0.0437. Yeah, 0.0437. I was concerned because I got theta is almost 1. That's not a small angle. Remember pi is 3.14, so pi over 2. So pi over 2 would be like lifting it by 90 degrees. Pi over 2 would be 1 something. So this is like 40 something degrees. So this couldn't be correct. So that would be a bad. It would not be a small angle. So anyway, so that number is correct. 0.0437 divided by L, which is 0.3 over 0.3. Now it is 0.146. 0.146 radians. I think that sounds reasonable. Let me check. Let me just check. 0.146, yeah, which is 8 something degrees, and that's a nice small angle. Less than 10 degrees usually. It's a pretty small angle and it's good. 5 degrees would be even better. So as long as you're not in like 15, 20 degrees, even 15 will be okay, but in the lab I will show you how it will deviate a lot. By the time you get to 20 degrees, you will start seeing large deviations. When I first learned about this formula here, I thought our teacher said, oh, you can use it to figure out the acceleration due to gravity, and I did it, and I was really surprised how close to 9.8 I got. So it says here, the period, omega is the square root of G over L. Let me just show you. Omega is the square root of G divided by L. And so the period would be, which is 2 pi over omega, is 2 pi, the square root of L over G. If you square both sides, you get this. Let's divide by 2 pi first. And so we get the square root of L over G. And when you square both sides, you get T over 2 pi, the whole thing squared, will equal to L over G. And so G will be L divided by this, so it will be 2 pi over capital T, the whole thing squared, times L. Because when you do L over this, it reciprocates. So what I did was, or what you do is you take a string and hopefully fix it somewhere on your window or something. You can measure the length, pull it by an angle that's reasonable, don't make it too large, maybe 10 degrees, and let it go. And don't let it swing just once, because if it goes back and forth, that's one time period, but your reaction time and so on will give you bad data. So what you do is you let it swing maybe 10 or 50 or 20 times, and you count. So you let it go, it goes 1, 2, 3, and then you stop your watch at maybe the 20th oscillation. So you get the period for maybe 20 oscillations, let's say, divided by 20. That will be the period for one oscillation. And plug it here, 2 times 3.14159 divided by the period that you just measured. Square the whole thing and multiply by the length. And you will see, you get something, 9 something, 9.5, 9.7, 9.8, 9.9, maybe 10. You get really good numbers for it. It will depend on how accurately you measure the length also. And you run into the problem of where do I measure the length from? Because you have a mass here, and you would measure to the center of mass. But usually the mass you have is probably something that's irregular shaped, but it's small enough that you can measure the length to here. So there will be an error in the length. The length will be whatever you think, plus or minus, let's say, a centimeter or something. So you can figure out how much error you made in the length, and then how much error in your reaction time. And then you can find that, let's say if the length you measured, and the error in the length is maybe, let's say, 5% in error, then you expect maybe your answer would be plus or minus 5% if most of the error is in the length. All right. Now, the next topic would be the physical pendulum. All right, so I'm going to write down the title. The physical. Earlier we did the simple pendulum where you had a point mass that's oscillating. What if you don't have a point mass? You have an actual object, extended object. Just show you here. Here's a meter stick. I pin it here and I let it oscillate. You see, there is mass here, 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 and all of it is oscillating. There isn't just one light string and one point mass attached to it. There is this whole thing stretching. So how do I calculate the oscillations here, the period of small oscillations and omega? That's my question. So let's draw something and continue. Here's the physical pendulum. So imagine you take a meter stick, any object that is, let's say my object looks like, all right, this. That's a bad drawing, but yeah, let me not be too ambitious and draw something creative. Let's say I have a baseball, something that is not very regular, like this, all right? So here is, let's say, the center of mass here. That's the distance to the center of mass, L. So it's the distance from the point of rotation to the center of mass, that is L. And I have mg. So the only thing that can cause the external torque, everything here, the fact that the pivot point pulls on this will not, the pivot point, first of all, it's over there. The distance from the pivot point to itself is 0, so it contributes 0 to the torque. So the only thing that's contributing to the torque will be this part of the mg. So here's theta. This is theta. So this part of mg is the mg sine theta. Notice when theta is positive, I measure theta from here. When it's positive, the torque is when theta is counterclockwise, excuse me, when theta is positive, the torque is negative. And when theta is here, when theta is negative, the torque is positive. So they're oppositely related. It's restoring again. So the torque would be the force, this component of the force, times the distance from the point of rotation to where the force is applied, and then it's negative. So I have the torque is I alpha, is I times alpha. And I will comment on what I is. So it is negative mg sine theta. And it's negative again because it's clockwise if theta is positive, it's counterclockwise if theta is negative. So it's always opposite to theta. And then this is the part of the force. The distance from the force to the point of rotation is L. And this is the moment of inertia. Now, what's the moment of inertia of this object? First of all, am I plugging in the moment of inertia of the object about the center of mass, or the moment of inertia of the object about this? It would be the moment of inertia about the pivot point. Okay, so it will be the moment of inertia about the pivot point. So I put I, and then here I have alpha. All right, and I think they call it just I pivot. Yeah, I would just put IP here for just to emphasize. It's not the moment of inertia about the center of mass. It's the moment of inertia about the pivot point. And alpha is the second derivative of theta with respect to time. So let's just write here negative mg. And if theta is small, this will be like theta, approximately theta. And here I have L, and the moment of inertia, P. And here this is the second derivative of theta with respect to time. That's what alpha is. And so we say d squared theta dt squared will equal to negative mg L divided by IP times theta. And this has the form of d squared theta dt squared equals to negative omega squared times theta. And we identify this part as the omega squared. And therefore omega will be mgl divided by IP square root. All right, and IP again is the moment of inertia about the pivot point. So here is an example. You have a student in a biomechanics lab measures the length of his leg from hip to heel to be 0.9 meters. And then it says, what is the frequency of the pendulum motion of the student's leg? And then let's assume that basically the student's leg is like a rod. It's not, but let's assume it is. So it is 0.9 meters. So we take the student's leg, it's like a long meter stick or something. And here it is. Here is the pivot. And we have L is 0.9 meters. And we're given the mass of the student's leg. Or actually, we don't even need it. Yeah, we don't need it. Yeah, we don't need the mass of the student's leg. So they say measure what is the period of small oscillation. So imagine this. Let me get the meter stick. So here is the student's leg, let's say, and you just let it hang, and then it goes back and forth. What is the frequency of small oscillations? So I can do it with my arm and just let it hang like this until it stops. There is damping, which we'll talk about in a moment. So what's the frequency of small oscillations if I just not apply any force on it, but just let it swing by itself? Well, we say here's the frequency of small oscillations would be mgl divided by p. Now, what's the moment of inertia for the student's leg? Well, we know that the moment of inertia about any axis, in this case axis p, would be the moment of inertia about the center of mass plus the mass itself of that object times d squared, right? Where d is the distance from the center of mass to here, the distance from the center of mass to there. And since the lag is a length L, so from here to here, d is equal to L over 2. And so I'm going to plug in L over 2 here. So I have I about the pivot. First of all, what's the moment of inertia for a rod about its center of mass? If you remember, you can look it up. It's 1/12 ml squared, and then plus the mass times d squared, but d is L over 2, and you have to square it. And so you get IP about the pivot will be 1/12 ml squared, plus this will become 1/4 ml squared. And a fourth plus 12ths, a fourth is 3 over 12. Let me write it as 3 over 12. 3 over 12. 1/4 is 3 over 12. So this will give me a common denominator. 3 over 12 plus 1 over 12 is 4 over 12, and 4 over 12 is a third, so I get 1/3 ml squared. 1/3 ml squared. And then I go here and plug it in. So I get omega will be the square root, the mass times gravity times the length, right? The mass times gravity times the length divided by the moment of inertia. And the moment of inertia is, oh, this should say 1/3, right? Not 1/13, 1/3. And then 1/3 ml squared. So this cancels. The 3 goes upstairs. One of the L's cancels. So I get 3g over L, like so. Remember, for the simple pendulum, where you just had a point mass swinging, it was the square root of g over L. It was the square root of g over L. But here, because you have a physical pendulum, the mass is not all at the end. Some of it, or it's incremented close to the end, farther to the end. So that's where the moment of inertia came into play. So that is omega. And if we plug in, if you like, you can plug in the numbers. So you get 3 times 9.8 divided by 0.9, 0.9. And you take the square root. And let's see what we get. With my calculator here. I almost plugged it in, but I made one simple mistake, I think. And that mistake was L here was the distance to the center of mass, not the whole length. So L, so in here I should have plugged L over 2, because the my L was this, but I should have the L in here. I should have called this one capital L, maybe the whole length. This one should be capital L, right? Capital L. This should say capital L. Let me just correct it. Capital L, capital L, capital L, capital L. And this should say capital L over 2. Capital L over 2. And this one should say capital L over 2 squared. And so you have this and this cancels. And let me see. Hopefully I have it correct in here now. Yeah, one in here I already had it. It's 1/3 ml squared. 1/3 ml squared. So just that's what happens when I try to go fast. 1/3 ml squared. Sorry about that. And this is just L over 2. L over 2. Let's do it slow. Let me do it in 2 more steps. Just 2 more steps. Almost there. So I have the mass canceled, so I have G and then L. This 2 I'm going to put downstairs, and this 3 will go upstairs, and then I have L squared, and then I have the square root. So now it cancels, and I think this should be, yeah, this looks more familiar to my eyes. Divided by 2L, and that looks good. Yeah, I think this looks good, yeah. And L is 0.9, and you plug in that, and let me plug it in. Okay. So I have 3 times 9.8 over 2, and then divided by L, which is 0.9, and we need to take the square root of all that stuff, and I get omega is 4.04. That's omega. Okay, so here's omega. That's omega. It's 4.04 radians per second. If you want the period would be 2 pi over omega, and that gives me, so let's do that, times 2 pi times 2 times 3.4, 1.9, it gives me 1.555 seconds. And then if you want the frequency, that's 1 over the period, and you get 1 over that, 0.643. 643 hertz. I think that's good. Yeah. So I'll stop here with the physical pendulum, and we're going to move on to damped oscillations. All right, just damped oscillations. And I think I'm running out of time on this video. I will pause this one, and I will see you in the next video.